Hello everyone. In today's lecture, we will discuss another important topic in the transient stability, that is the swing equation. That swing equation is generally the equation which are used to finding out the synchronization between the synchronous generator and the synchronous motor or the load that are connected to the infinite bus. Okay, so here is the power flow of that in the synchronous generator. Power flow of power in the synchronous generator, where we have to observe it's the PM. It's the mechanical input that are given to that say mechanical input, whereas PM it's the mechanical torque. Omega S is the synchronous speed, whereas TE it's the electrical torque that are generated that is across the prime movement, and PE is the mechanical, so electrical power that are generated from that generator. Okay, so to consider the generator, synchronous generator, developing the electromagnetic torque, that is a TE, corresponding to the electromagnetic power PE, electromagnetic. So that torque PE, TE, and the PE, it's a with all about the parameter related to the electrical content characters, electrical parameters, while the operating at a synchronous speed omega s. Whereas in terms of that, whereas in terms of that mechanical one, the input torque, input side, the input torque is equal to Tm, input torque that is a Tm, that is a mechanical torque, it's provided to the prime mover at a generated shaft, that is it's a Ti. So ये क्या हो गया, Tpm बोल सकते हैं इसको, या फिर Ti बोल सकते हैं, Ti or the Tm, that is equal to Ti I or Tn, and that is equal to Pm or the Pi, without any disturbance under the steady state condition. Okay, now we have to finding out the relation between that is Pi with respect to the Pe, that is the mechanical power with respect to the electrical power at a synchronous speed, without any disturbances occurring. Okay, so under this condition, that is we all know that is nothing but the mechanical without any disturbance, there is a no losses should be there. Means what, the energy generated at the sending it, we are the same energy we are getting at a receiving it. So thus the TE is equal to TI or the T is equal to TI. I bolo ya fir M bolo, one of the same. Okay, so here we neglected any retarding torque or like the rotational losses. Therefore, TE into omega S, that is the PI P E is equal to PM. Therefore, the electrical power is equal to mechanical power. Therefore, TE into omega S is equal to TI into omega S. Okay. So equal to is equal to PI is equal to P is equal to, so their difference is equal to 0. Now the change in the load or the fault is the occur. Okay. अब क्या करना है? Now the load changes or the fault occur, and under this case the PI is not equal to the P. Therefore, the left side of that equation is not equal to the 0. Means what, that equation should not be equal to 0. And that accelerating torque comes into the play. Means what, accelerating power is not with the rate of change with respect to the power. So that PA is nothing but the accelerating power is equal to PI is equal to PI minus P is equal to M d squared theta E upon dt square plus D into the D d by dt of theta E, that is the electrical angle position, is equal to PA. So the PA is equal to acceleration, that is PI minus PE. If the acceleration कब possible होगा, जब electrical power is when the mechanical power should be more as compared to the electrical power, then the deceleration, and the electrical power should be more than the acceleration. Okay. So under this condition, where the M is nothing but the moment of inertia, where D is nothing but the electric damping coefficient across the change of that angular position. So it is more convenient to measure the angular position with respect to the synchronous rotating frame. Therefore, that del is equal to theta minus omega t. That is the under the rotating synchronous frame. Thus, that d square theta e upon dt square is equal to d square del upon dt square. Okay, so just we replacing this equation, that is del is equal to the power angle of that synchronous frame. Thus we replacing in the equation number 13. The equation number 13, and that neglecting the damping. So we are getting is equal to M d square del upon dt square is equal to Pi minus P. Okay, Pi minus P is equal to Pa. Okay, so now the as we all know that M is equal to what? Using the equation, say m is nothing but the 6 and the 16. What is the equation number 6? That is p. What is the m? Moment of inertia. Moment of inertia is equal to क्या होगा? G h upon pi upon f. G is nothing but the gravity, and h is nothing but the inertia constants. G into h upon pi into f. D square del upon dt square is equal to pi minus pe, where the g dividing the throughout the g through the MVA rating of that machine. That is MVA rating, that is nothing but the thus m is equal to mpeu d square del upon dt square is equal to pi minus PE, where the in terms of the m moment of inertia in the per unit is equal to what? It's a g upon h upon pi into f. So therefore, h upon pi into f d square del upon dt square is equal to pi minus pe is called as string equation. Instead, but it generally used to finding out the stability or how much power we are getting under the accelerating one or the deaccelerating one or the accelerating power के अंदर अपने को how much power we are getting under the rotor dynamics of that synchronous motion. So thus the swing equation are generally used to finding out the rotor dynamics of the synchronous machine, whereas damping can be decided by the dynamic stability studies. So here the damping should be neglected. So under the damping must be considered under the dynamic stability of that power system. Okay, so this is all about the swing equation. The next lecture will discuss all about the application, the point-to-point calculation of that swing equation under the different condition. Okay, thank you so much.